Estimating a population mean. Our objectives are to obtain a point estimate for the population mean, state properties for student t-distribution, determine the t-values, construct and interpret a confidence interval for a population mean, determine the sample size needed to estimate the population mean within a specified margin of error. Obtaining a point estimate for the population mean. A point estimate is the value of a statistic that estimates the value of a parameter. In the previous section, we used the sample proportion to estimate the population proportion. In this section, we're going to use the sample mean to estimate the population mean mu. Obtaining a point estimate. Let's look at the first example here. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represents the weights in grams of 17 randomly selected pennies minted after 1982. So here is the set of data. Treat the data as a simple random sample. Estimate the population mean weight of pennies minted after 1982. So in order to estimate the population mean weight of pennies minted after 1982, we're going to obtain a point estimate, which is the sample mean. So to compute the sample mean, we add all of the weights of the pennies, 17 weights of the pennies, and divide that by the number of pennies. We will get 2.464. So a point estimate for the population mean mu is going to be the sample mean x bar equals to 2.464 grams. So we obtained the point estimate. Now, if we stop at this point, this might not be a good representation of the population mean. However, we will be able to create a confidence interval where we are, let's say, 95% confident or 99% confident that the population mean happens to be within a range of this number. And this number is going to help us create that range of data that we are confident that it will contain the population mean. The student t-distribution. So, what is the student t-distribution? The student t-distribution, commonly known as the t-distribution, is the probability distribution that plays a critical role in statistics, especially in situations where sample sizes are small or when the population standard deviation is unknown or not given. It's developed by William Seeley Gossett under the pseudonym student. This distribution is similar in shape to the normal distribution, but has heavier tails, which means it accounts for greater variability in data. The t-distribution becomes particularly useful in hypothesis testing and confidence intervals, which is we're going to use it for today, and regression analysis, where we work with sample data rather than the entire population, which is what we have access to here is a sample data. We don't have access to the population data. It is characterized by its degree of freedom, n-1, which affects the shape of the distribution. As the sample size increases, the t-distribution approaches the normal distribution, making it a versatile tool to inferential statistics across various fields. So, suppose that we have a simple random sample of size n, and that is taken from an entire population. The population from which the sample is drawn follows a normal distribution. So the distribution t, which is, we computed before the z-score for the distribution of sample proportion, and we said the z-score for that is basically the sample proportion minus the population proportion divided by the standard error, which is p naught times 1 minus p naught divided by the sample size. And also, we computed the z-score for the distribution of sample means, and we said that is equal to x bar minus the population mean divided by the population standard deviation divided by the square root of the sample size. But when we are dealing with samples, usually we do not have access to the standard deviation, the population standard deviation, so we would replace that with the sample standard deviation instead of the population standard deviation, which is going to change the name from a z-score to a t-score. So that is what distinguishes this formula from that formula. This distribution follows a student t-distribution with n-1 degrees of freedom. So this is going to follow a student t-distribution, or basically a t-distribution with n-1 degrees of freedom, because we do not have access to the information from the population, but we have the sample size and we have the sample standard deviation instead. Now, if we create a simulation where, let's say, obtain 1,000 simple random samples of size 5 from a normal distribution with a mean of 50 and a standard deviation of 10, then we can determine the z-score, which is x minus mu divided by the standard error, versus the t-score, which is x minus mu divided by, we replace the standard deviation from the population with the sample standard deviation. If we draw a histogram for both the z-scores and the t-scores, this is what we're going to see. Here is a histogram from the z-score, which is, as a reminder, the z-score is x bar minus mu divided by the population standard deviation divided by the square root of the sample size. You will notice that the population is normal. The shape is bell-shaped and the tails are short, and it is approximately normal. Versus if you draw the histogram for the t-distribution, you will notice a big difference here. So the shape is approximately normal. However, what you notice here, you will notice that the tails are a little bit heavier than the tails of the normal distribution. So as a conclusion, we say that the histogram from the z-score is symmetric or bell-shaped, and it is centered about the 0, similar to the normal distribution. And virtually all of the rectangles between -3 and 3, meaning the tails are very short. They're not as heavy. Notice here, the tails are not very long and heavy. Meaning the z-distribution follows a standard normal distribution. That is what we expected. While the histogram from the t-distribution, or the t-scores, is also symmetric about the bell, similar to the normal distribution, the center of the distribution is about 0, so that is similar to the normal distribution as well, but the distribution of t has longer tails or heavier tails. They are more dispersed because the t-scores are more dispersed in this case. Also, it is unlikely that t follows a standard normal distribution because of that trait. The additional spread in the distribution of t can be attributed to the fact that we use the sample standard deviation instead of the population standard deviation. And because the sample standard deviation is itself a random variable rather than a constant, such as the population standard deviation, we have more dispersion in the distribution of the t-scores. And that is why we have the heavier tails. So what are the properties of the t-distribution? The t-distribution is different for different degrees of freedom. So when we have different sample sizes, we're going to have different t-scores for the same level of confidence. The t-distribution is centered about 0 and symmetric about the 0, so that is similar to the normal distribution. The area under the t-curve is 1, and the area under the curve to the right of 0 equals the area to the left of 0, which is equal to 1/2 or 50%. And that is also similar to the normal distribution. As t increases or decreases without a bound, the graph approaches but never equals to 0. That means the tails are going to expand and increase, but they will never approach 0, similar to what happens to the normal distribution. The area in the tails of the t-distribution is a little bit greater than the area in the tails in the standard normal distribution, because we're using the sample standard deviation instead of the population standard deviation, or to estimate the population standard deviation. The sample standard deviation is a variable it's going to depend on the sample size, but the population standard deviation is a constant, thereby introducing further variability into the t-statistic. As the sample size n increases, the density of the curve of t gets closer to the standard normal density curve. This result occurs because as the sample size n increases, the value of the sample standard deviation gets closer to the value of the population standard deviation by the law of large numbers. And here is a comparison between the increasing in the t-distribution and the normal curve. The curve that is blue, the first curve right here, is basically when n, the sample size, is equal to 5. When the sample size increases, notice how we have the purple curve here, which is becoming, the tails become a little bit more narrower, and the normal curve and the curve here approaches the normal curve, which is the last curve right here. As you can see, so when the sample size increases, the t-distribution becomes an approximation for a good approximation for the normal distribution. How do we determine the t-values? We use the notation t sub alpha to indicate the t-value such that the area under the standard normal curve to the right is alpha. So if we want to find t sub alpha here, which basically represents the area to the right of alpha, to the right of t sub alpha, and that area is equal to alpha. Finding the t-values. Find the t-value such that the area under the t-distribution to the right of t is 0.2, assuming 10 degrees of freedom. That is basically finding t sub 0.20. In other words, here is the distribution, and we want to find t sub 0.20, which means this area is 0.20. So in order to obtain that, we're going to basically, so here is the shape again. So we will need to obtain the area to the left, which is 1 minus 0.20. So that is 0.80. We need this area to the left so we can use the t inverse function. So in this case, we're going to use the t inverse function. So t sub 0.20 is equal to, so we're going to use the Excel command t inverse of the area to the left of t, which is 0.80, and then comma the degrees of freedom should be given as well. So that is how you're going to compute the t-score using Excel, and you will end up with the number 0.879. Now that we know how to compute the t-scores based on the given area to the right, we will be able to estimate a population mean using the t-distribution in this case. The approach of finding or constructing a confidence interval relies on the sample mean and the sample standard deviation. So because we do not have access to the population data, otherwise we wouldn't need to estimate a population mean to begin with. So because it relies on the sample mean and the sample standard deviation, we're going to use the t-distribution and degrees of freedom based on the sample size. And we have to make sure that the sample size come from a simple random sample or randomized experiment. The sample size is small relative to the population size. That is, the sample size is less than or equal to 5% of the population size. So that is what this notation means. And the data comes from a population that is normally distributed or the sample size is large. And here are the steps. We're going to construct a confidence interval, 1 minus alpha times 100% confidence interval for the population mean by using these steps. We're going to compute the lower bound, which is basically the point estimate. It is point estimate minus the margin of error. The margin of error in this case is equal to the t-score of alpha divided by 2 times the standard error, which is standard deviation divided by the square root of the sample size. The point estimate is going to be x bar, so we're going to have x bar minus t sub alpha divided by 2 times s divided by square root of n. That is the lower bound of the interval. To find the upper bound, we just change the minus into plus, and we obtain the upper bound of that interval, confidence interval. So t sub alpha divided by 2 is basically the critical value with n minus 1 degrees of freedom, and we will know how to compute that in the next steps. So here is an example. We will use Excel to simulate obtaining 30 simple random samples of size n equals to 8 from a population that is normally distributed with a mean of 50 and a standard deviation of 10. We want to construct a 95% confidence interval for each sample. How many of the samples result in intervals that contains the populations the population mean in this case. So what does it mean to have a confidence interval? So with the simulation, you notice here we obtained the first sample with the mean of 47. That is the sample mean, by the way. And notice how we build a confidence interval of 95%. And that interval contains the population mean 50. The next one contains the population mean 50. That contains also that one contains. However, sample 8 doesn't contain the population mean. So we have one sample here that doesn't contain. We continue simulating and we notice all of these intervals will contain the population mean. However, if we reach sample 28, you will notice that this interval does not contain the population mean, which is 50. It starts after 50, so 50 is outside of the range of this confidence interval. What we conclude from this simulation, notice that 28 out of the 30, or in percentage, is 93% of the confidence intervals will contain the population mean 50. In general, for a 95% confidence interval, any sample mean that lies within 1.96 standard errors of the population mean will result in a confidence interval that contains the mean. So out of 100 confidence intervals, we expect with a confidence level 95%, we expect that 95% or 95 of the intervals will contain the population mean, while only 5% will not contain the population mean. So that is basically the meaning of the confidence interval in this case. Whether a confidence interval contains the population mean depends solely on the sample mean X bar. Let's look at the process of computing a confidence interval about the mean. So let's say we want to construct a 99% confidence interval about the population mean weight in grams of pennies minted after 1982. We're assuming that the sample standard deviation is 0.02 in this case. So we were given raw data. We're going to first step, we're going to compute the mean and sample standard deviation. We can also compute the standard deviation as well. So in the next slide here, we computed the mean. The mean X bar is equal to 2.464 and the standard deviation S is equal to 0.02. You can round it to 2 decimals. Using this information also, we obtained a distribution for the weight in grams of pennies, and notice how it is not normally distributed. However, it is approximately normally distributed. It's a little bit skewed to the right. And that doesn't matter because we're going to use the t distribution in this case because the population standard deviation is not given and we do not know anything about the population mean. So the first step here is we have a 99% confidence level, which means alpha is 1% or 0.01. And if we want alpha over 2, which is basically we want the area in the middle, so we want to compute the critical value that separates the middle 99% from the rest of the data. That is alpha divided by 2. We will divide 0.01 divided by 2. We will get 0.005. So we want to obtain t sub 0.005. And using Excel, we're going to use t dot inverse of 0.005, comma, the degrees of freedom is 16 in this case because the sample size is 17. So degrees of freedom is 17 minus 1. You will get the number 2.921. That is going to be the critical value. What else do we need? We need the mean and the standard deviation, and we computed that from our raw data. We concluded that X bar is equal to 2.464, and the standard deviation S, the sample standard deviation, is 0.02. So to compute the lower bound, we're going to say that is X bar, which is this number, minus t sub alpha divided by 2, which is we computed right here, times S divided by square root of the sample size. So if you do the math, you will end up with 2.450. That is the lower bound of our interval. Similarly, you're going to compute the upper bound, except for instead of subtracting, you're going to add, and you will end up with 2.478 as an upper bound. So the interpretation goes like follows. We say we are 99% confident that the mean weight of pennies minted after the mean weight here, we're talking about the population mean, the mean weight of pennies minted after 1982 is between 2.450 and 2.478 grams. Okay, so we are confident, we're 99% confident that the population mean weight of pennies is between the lower bound and the upper bound of our confidence interval. And that is how we're going to compute the confidence interval basically. If we want to just compute the margin of error, then the formula for the margin of error is going to be the following. T sub alpha divided by 2 times S divided by square root of the sample size. So that is the margin of error. We basically compute this part of the lower bound or the upper bound, and that would be the margin of error. The last but not least concept that we need to figure out is to determine the sample size needed to estimate the population mean with a specified margin of error. So if we would like to estimate to determine the sample size required to estimate the population mean mu with a level of confidence 1 minus alpha times 100% with a specified margin of error, that means the margin of error has to be given and the level of confidence has to be given, and the standard deviation, the sample standard deviation has to be given as well. We can use using this formula. We can do so using this formula. Notice how in this formula we substitute the t-score with the z-score in this case because we have no access to the sample size and the t-score depends on the sample size. So we're going to estimate the t-score with a z-score. They are very, very close to one another, and that should give us a good estimation of the sample size. It's not going to be precise, of course, because the z-score is not the same as the t-score, but the numbers are going to be very close to one another. When you compute the sample size, the answer should be rounded up no matter what the fraction or the decimal after the point is. For example, if you have 125.1 or even 0.1, then you're going to round that up to 126. So no matter what fraction you have here, you're going to always round it up. You're going to round your answer up to estimate that sample size. Also, it's worth to mention that when you compute the z-scores, it is a good idea to round the z-scores to 3 decimals to be consistent throughout. Although not rounding the z-score is going to result in different sample sizes, especially if the sample size is huge, it's going to give you a huge difference between the rounded z-score and the unrounded z-score. So make sure that you round the z-score to 3 decimals when you are using it to estimate the sample size, just to be consistent across the board. Here is an example. Determine the sample size. Back to the pennies again. How large a sample would be required to estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with 99% confidence, assuming that the sample standard deviation is 0.02. So what do we have here? We have the margin of error, or E, is 0.0025. Sometimes we say margin of error, ME. Sometimes we say BME. Sometimes we say just E. And we have the confidence level is 99%. And we have the sample standard deviation is 0.02. So we have everything we need to compute the sample size. Now the process. The first step is to find alpha divided by 2. So alpha in this case is 1 minus the level of confidence, which is 0.01. And alpha divided by 2 is 0.01 divided by 2, which is 0.005. Now to compute z sub alpha divided by 2, which is z sub 0.005, we use the normal distribution because z-scores follow normal distribution. So we're going to say norm dot s dot inverse of 0.005, and that should give us 2.575. Again, we're going to round to 3 decimals here for consistency. And then we're going to apply the formula given here. So n equals to z sub alpha divided by 2, we computed that, times s is given, divided by the margin of error. If the margin of error given as a percentage, make sure you turn it into a decimal before using it. And then you're going to divide and then round your, then you're going to raise your answer to the second power or square your answer. So the answer here is 106.09. We're going to round this number up. So it's going to be, the required sample size will be 107. And that concludes the estimating of a population mean. We know now the t-distribution. We know how to compute the t-distribution. We know how to figure out the margin of error and how to construct a confidence interval and interpret the confidence interval. And we know now how to determine the sample size needed to estimate a population mean. So if you have any questions regarding these concepts, please let me know. And make sure that you do your homework, watch the videos posted, and use the help of Stats Calculator that I provided for you in order to obtain all of these information. Again, if you do have any questions, please let me know.